All right, here we go. Hopefully that's working. By the way, just for the record, my recording in my last class of the day on Wednesday failed. Sometimes something goes wrong with the computer or something. And so anyway, that may happen sometimes. Hopefully not. Hopefully it's rare. And looks like this seems to be working fine, but fingers crossed. Okay, so last time we were talking about graphs, right, as a way to draw pictures to help us get a geometric intuition for what functions are doing. And we talked about the construction last time. The big idea is that you take inputs and the corresponding outputs, right? And then you turn those, list those as coordinates of the same points. That then, if you go over all possible inputs, you get, a whole bunch of points that look like this, and that will make sometimes a curve, sometimes a surface, depending on, what your domain is, what your target is, etc. Okay, so we saw these examples last time, and the sort of an alternative way to think about it that I noted was you can think of this as what the function is doing is it's kind of like it's taking the domain, which you sort of visualize down here, and it's like the function is telling you how far to push upward or downward, right, to produce then the resulting curve. Color change. The resulting curve. So, not surprisingly then, the dimension of the domain should be telling you what the dimension of the actual graph itself is. And so here, looking at this, our sort of first example, the kind of example everybody's seen before, because we have one input variable, that's why the graph is a curve and therefore one-dimensional. Right. And then by analogy, same story for down here. If we're looking at a two-dimensional domain, as we are here, got a two-dimensional domain. Then the function is telling us how far to push that upward. That's telling us, again, the function is telling us what the z coordinate should be, namely how far to push it up. Again, though, since we start off with a two-dimensional domain, then as we would expect, we end up with a two-dimensional graph, aka a surface. Okay, is everybody with me? All right. Okay, so graphs are good. I like graphs, but they are not the end-all, be-all of drawing pictures of multivariable functions, and not by quite a bit. Now, these pictures here look pretty all right? What's the problem with these? I mean, I can deal with this pretty nicely. But now let's just take one more additional step, and instead of one input variable or two input variables, let's now consider what happens if we have three input variables. Function from R3 to R1. Right? So as we say, real valued, because the outputs are real numbers. Multivariable function with three input variables. And, here's the thing. We've got three input variables, and we've got one output variable. And so altogether, our graph is going to consist of points with four coordinates, aka our graph lives inside of four dimensions, which we cannot even pretend to be able to draw. Right? Does everybody see that? That's this is bad, right? This is a bad news situation. So, looking back on it then, while, graphs were just fantastic in when we're talking about single variable functions, there's really only one other scenario in which we can even pretend to be able to draw a graph, and that's the ever so slightly more multivariable, where we have two input variables. And even then, I'm going to say that this is not a great picture. This is, we're doing the best we can under the circumstances. I've tried to make it look like this is a three-dimensional picture, but this is a two-dimensional screen I'm drawing it on, right? It's not really a three-dimensional picture. Furthermore, you may feel like you see that there's a surface in here, but your imagination is doing some pretty heavy lifting there. right? In fact, I have not actually drawn anything in this entire region here. I've drawn nothing. And so it's just kind of what I've drawn around it that's you're kind of making you feel like you're seeing something there. So I'm going to say I have kind of pretended to draw the graph here. Even there, I didn't really, right? This is a poor representation. Certainly not as true of a picture as this is. So graphs are what I like to call dimensionally expensive. Right? They use all the dimensions that they can possibly use. And when we're dimensionally constrained, as we are three-dimensional critters trying to do math, right? Being dimensionally wasteful is, we just don't have the dimensions to spare sometimes. So we're going to have to look for other alternatives, other ways to visualize functions, because very often, and look how tame this example would appear to be at the outset, there's only 3 input variables. It's not that bad, right? And yet we can't draw the graph. Okay, so this leads me to a couple of points. I've already kind of made this second point down here, which is that there's other ways we're going to be drawing pictures. We have to have other ways to draw pictures of multivariable functions, because the graph just isn't going to cut it, right? So we are going to have these other kinds of pictures, and so it becomes very important now all of a sudden. Not so much in single variable calculus, but we're going to have to be very careful. Do not conflate a graph with the function whose graph you're looking at. In single variable calculus, you can get away with this because graphs are the only kind of pictures that are to be talked about. And if you say function when you're actually talking about the graph, well, there's no other picture to confuse it with. So no possible confusion is just not a problem. But we're going to find that when we are looking at a function, we're going to perhaps sometimes be looking at its graph. Sometimes we'll be looking at its level sets. Sometimes we'll be looking at its image. There's different kinds of constructions, different kinds of pictures that we're going to draw. And if you say graph when you mean something that's very importantly not a graph, then that's going to create serious confusion and lead to problems and mistakes, etc. Okay, so this is a challenging task. I know you've got many years under your belt of when you see a graph, you're thinking that's what the function is, and so you're going to have to break several years of habit of saying function when you mean graph, or saying graph when you mean picture, or something like that, right? And so good luck, and it's something you're going to have to exert some effort on. Okay, sorry about that. Okay, here's another picture to represent a function, and you'll notice that I'm starting off with the category of function that failed miserably on the previous page as we were trying to draw graphs, right? So we're going to show this is an option of something you can do, pros and cons, but in a situation where a graph is not on the table, right, this can be useful. And this is what I like to call the literal picture, and I say literal because we're going to take what the function is directly doing, right? It is taking points in R3. Well, I'm going to draw a picture of R3 there. And it's going to return points in R1. So I have a picture of R1 over here. And what the function does, the function takes points out of R3 and then plops them down in to R1. So, I think it's pretty reasonable to say this is a literal picture because, it's just a picture of the action of what a function does. And so, for example, notice that we've got this point here, A in R3, and we have a representation of sorts here of what the function does to it. The function takes it to that point, f of A. Now, let me gripe about this picture. There's a lot to gripe about on this picture. For one thing, where's the shape? I don't see a curve. I don't see a surface. I don't see any, what am I supposed to, where's the geometric intuition of, I see just one point there and it goes to one point there. That's not very helpful. And granted, yeah, that is it's not as awesome as this picture is. Sure, absolutely. But this is a beggars and choosers situation, right? We don't have just all the dimensions we could possibly make use of, and we do whatever we please with dimensions. We're out of dimensions, and we have to be careful and judicious with how we use the dimensions. And this, while it's not a very good picture, it is a picture, right? And you got to give me it's better than what we had here, which was absolutely nothing. Right? Does everybody see that? All right. So, in fact, there are some really nice things about this picture that we haven't gotten to yet. What we're going to be doing in a multivariable calculus class is we're going to be asking questions like, all right, well, look, I'm here in the domain. And what happens if in this domain I take off and start moving with some velocity, v? And then we could reasonably ask, all right, well then the image that was here, if I move the input, wouldn't we expect resulting movement in the output? Right? And so we're going to be asking questions such as, how do I relate this input velocity to that output velocity? And notice that, again, it's not that the picture answers that question, but it's that the picture allows me to draw a representation of the question itself, right? And that has value, right? And it turns out there's going to be a very strong relationship between the input vector v and this output vector that I am deliberately not naming. We'll have a really good name for it later. Okay. All right, so again, it's what I call the literal picture. Very useful sometimes. Okay, level sets. This is another kind of a picture. It's a completely different construction. I cannot emphasize enough. This is not the graph construction. The graph construction was this thing back here where you take the inputs and you take the outputs and you plop them down together as coordinates for the same point, right? Or you might say differently, the graph is where you set, let's see, I'll come down to, let's say, this picture here. The graph of a function is where you take the function and you set its values equal to a new variable, thus giving you an equation in more variables. Okay. So with graphs, we set the function equal to a new variable. With level sets, where am I? Here we go. With level sets, we set the value of the function equal to a constant. Very different. This is not a variable. There is no b-axis. Right? So we're setting the values of the function equal to a constant, or sometimes several constants. Okay. Now, I'm going to draw some pictures in a second here. A couple of quick things to say. First of all, you can think of this as being a preimage. After all, the level set is the collection of points that when you put them into the function, give you the fixed output value. So they are literally input values to the function, and thus we use the term preimage, right, per last time. Also notice, whatever that output value is, right, the preimage, the level set, can be described with this notation, because after all, we are taking the output value and asking, okay, but what are the corresponding input values? It's like we're kind of sort of going backwards through the function, and thus the F inverse notation. And now, to be fair, this is not a function. F inverse is not. This function is not invertible, probably, right? N and M are different values, and it's probably not invertible. But nevertheless, this notation, as a notation, communicates the idea of going backwards. So it's very common. Okay, let's get our hands dirty and see an example. Here we go. I have a function from R2 to R1, and we know how to draw the graph of functions. But here, again, that's not what we're doing. Level sets. We take an output value, for example, 1, and I ask, what are the input values that would give me that value 1, right? So I want to know, where's my thing? Here we go. What are the points over here in the domain that when I plug them in to the function, the output becomes 1. All right. Okay, well, if I want to know when f is equal to 1, I can just literally write that down. Let's see here. Here's f. And I want to know when that's equal to 1. So this equation here describes my my level set, what we call a level set. We'll talk later about why it's called a level set. Good news, that equation's familiar, right? X squared plus y squared is 1. I know the deal there. And so let me get my color coding back on track here. So for this output value 1, when I'm trying to find f inverse of 1, I want the function to equal to 1. The set of solutions is this circle. That's the set of inputs that gives me that output. How we doing? Everybody on board? Okay. Yeah?
How would the graph of that look like?
How do what now?
How would the graph of that look like?
The graph of this function? Yeah, we'll get to that. It's actually, well, now it's 2 inputs, 1 output, so we know it's a 3-dimensional picture. 2 inputs means it's a 2-dimensional thing, namely a surface. And yeah, we're going to talk about how to draw how to draw pictures, solution sets of certain equations when you have 3 variables. Loosely speaking, I mean, just to give you a real short answer, it's a great question, by the way. Of course, here's what the equation of the graph looks like. Right? Graph meaning new variable. And I'm just going to kind of appeal to your geometric intuition that, well, kind of in, if you will, in the x direction, it's kind of parabolic, right? But then also, if you will, loosely speaking, in the y direction, it's kind of parabolic. And so, if you ask yourself, you know, what shape can I think of that's kind of parabolic in the x direction, but also parabolic in the y direction? It's going to be kind of a bowl sort of a shape. Yeah, does that make sense? Yeah, but we'll talk in more detail about that in a few minutes. Yes.
So does this essentially show cross-section of the bowl?
That's a great question, and I'm going to talk about that in detail on the very next page. Yeah. Great thought. Absolutely. Okay. Okay, so there's one of our level sets, and now let's see the next level set real quick. We'll look at a different output value of 2, and so we want to know for that, what is the level set corresponding to 2? We want f inverse of 2. We want to know where the value of the function is equal to 2. Value of the function, of course, still being x squared plus y squared. Right? And then we look at this resulting equation, and that equation there is the equation of another circle, slightly larger circle. And so you can probably notice the pattern here, and I claim for all positive output values, we're going to have circles as the level sets. Okay. All right. So now let's do a little quick compare and contrast. Here, these are what our level sets look like to try to understand this function. Now, we've previously, though, drawn a picture of a function from 2 inputs to 1 output. And let me flash back over to here. What did our previous picture look like? Well, it looked like this. And pros and cons, really. I mean, there is something very satisfying about seeing the graph. I feel like I'm seeing a surface there, but I've already complained I didn't really draw a surface. I made an illusion that suggests a surface. I didn't really draw a surface. After all, this is a pencil. Right? I draw only the curves is all I can draw with this thing. So this picture leaves a lot to be desired. Furthermore, it's hard to draw 3-dimensional pictures. Right? Even if you're good at it, it's hard to do. Whereas, by comparison, here, I have a 2-dimensional picture that I'm drawing on 2-dimensional paper. The picture itself is a 1-dimensional curve that I'm drawing with a 1-dimensional pencil. It's perfect, right? It's a match made in heaven, at least in terms of the actual drawing of it. So even though it doesn't really tell you the same information that a graph does, it's really nice in some important ways. Everybody happy? Okay, here's an example where y'all have seen level sets previously. At least you may have, may not, but you may have. If you've ever gone hiking, or if you've ever looked at a what they call a topographical map, right? That attempts to show the shape of the land, maybe around a mountain or some hilly area or something like that, then you'll recognize these things called contour lines. And what defines a contour line is contour lines are where the altitude function is set equal to a constant. Right, so this purple line that I've drawn there, that represents altitude equals some value. I don't know, let's say 500 feet, something like that. And then, of course, that one line might not tell you the whole story, probably doesn't. So typically they would draw several. And so maybe they start with, okay, there's, let's say, 300 feet, and there's 400 feet, and let's see here, here's 500 feet, and then here's 600 feet, and then you notice the pattern, here's 700 feet, and then maybe here's 800 feet, and you start to get a pretty good picture that's, I kind of see what the shape of that mountain is. Now, of course, there's another way that we could represent a mountain, and that is I could draw the graph of the altitude function. The thing is, the graph of the altitude function around a mountain is the mountain itself, or a three-dimensional model of the mountain, and you can't fold that up and put it in your pocket and go for a hike, right? Two-dimensional picture, you can fold it up in a pocket and go for a hike. Or see it on your two-dimensional phone screen, or what have you. All right. So this is useful in a lot of ways. One of the big rules if you're hiking is, unless you're just a glutton for punishment, is try not to cross too many contour lines too fast. Right? So if you were going to hike from, let's say, from here to the top of the mountain, which is there, it would be very challenging to just go straight at it. You're going to climb straight up the very steep, almost cliff-like shape. And what I would do instead is I would kind of go around. Oh man, hopefully I wouldn't do that. But I would go around kind of like this, and I would go up this nice gentle slope like that. Much easier. Right? And again, the map allows me to make this realization because the map shows me where the contour lines are. And in that path I chose, I didn't pass that many contour lines that quickly. So this would be not very steep. Much more my speed. I have another example of this. So this is a actual contour map, topographical map, showing a location called Mount Evans. This is in Colorado, and side note, it's, as I understand it, it certainly was and maybe still is the highest paved road in the continental U.S. And by the way, side note, it's a heck of a drive. It's very unnerving. There's no guardrails. The road is not in good shape. And you're approaching up to the top of the mountain. The road stops at over 14,000 feet. And oxygen is thin, and your brain does not work right. Well, anyway, your brain doesn't work right. Let me leave it at that. And so here it is. Your brain is not working right. You're on this terrible road, very steep. There's a 1,000-foot drop over on the side. There's no guardrail, and you're confused. Right? So it's very unnerving. I'm pretty sure I've done it for the last time. Anyway, look at the nature of the road, right? And so why didn't they they pave the road like this? Oh, well, that's just bonkers steep. Probably no car could even actually do that. Maybe some hardcore, Jeep or something, right? But that's a rough drive. Certainly my car couldn't do that. But so notice they do this thing. These are called switchbacks. Right? And the idea of the switchbacks is that you don't cut directly perpendicular to the contour lines. You kind of mostly follow the contour lines, but maybe then just angle, off of the contour lines in the uphill direction just a little bit at a time. And of course, you can't do that forever. You're trying to get over to here, and so you have to then turn around and do the same thing but in the other direction. And so again, you can see why they would make the roads like this because of these contour lines, aka level sets. Everybody good? Okay. Alrighty. Okay. Oh, whoops. Oops, here we go. Yeah. Okay. So now somebody asked a great question earlier. I think it was you. That is there a relationship between graphs and level sets? And yes, there is. It goes as follows. Suppose you have a function, and I'm just going to do the example here of if we have two input variables. If you form the graph of that function, keep in mind the rules for graph. Set the value of the function equal to a new variable. Right? Okay, fine. Now, on the other hand, you could make level sets by setting the value of the function equal to a constant. And those are different, right? A variable is not the same as a constant. But here's the thing, and easy to see it once you see it, but if you set the function equal to a new variable, and if you set that new variable equal to a constant, then in effect, you're, in practice anyway, effectively kind of setting the function equal to a constant. And so you would expect then that would be the same. So now let's say that though in different language. What this means is if you take a cross section, right? Z equals a constant means I'm slicing horizontally like this. If you take a horizontal cross section of a graph, that gives you a level set. In this case, a level curve. So that's what we have here, and you'll see I've written it out in English here. Level curves are horizontal cross sections of graphs. Or said differently, this algebra is summarized by this pithy little sentence. Everybody with me? Okay. All right, let's see an example of this. And, oops, read that. So again, this function we've dealt with previously. We've already drawn the level sets. And reminder, level sets are when you set the function equal to a constant. And that gives us these equations, which of course are these circles. So level sets are circles previously noted. Now let's draw the graph. The graph of the function, again, setting now the function equal to a new variable, not a constant. That gives us this equation, which, again, we're going to study this in greater detail in a couple of minutes. But for the moment, as I hand waved to you before, it's kind of curving up in the x direction, it's kind of curving up in the y direction, and, you kind of expect that graph to look like this. Now, before I finish this example, I do want to pause and take a quick notice of the fact that, as previously warned, notice that the level sets and the graph, these are very different pictures. Very different picture. And if you were to refer to this as being the graph of the function, that's a wildly inaccurate statement. It's severely wrong. It's not the graph. It's a picture. It's not the graph picture. So again, be very careful with your language, please. Okay, so now as finishing up the example, if we take now the cross sections by setting z equal to various different constants, take these cross sections with these equations, then as predicted, cross section of graphs are indeed level sets. Everybody good? Yep.
So how would a level set look like? Right now the graph is like this, but what if it was like upside down? Would it be the same?
Oh, yeah, that is one of the shortcomings of these kinds of pictures, and let me answer in the context of altitudes. I mean, maybe this looks as a mountain, but as far as I know, it could be a hole in the ground, right? And so, yeah, that's right. That's a shortcoming of you can't really tell from the picture. If you really wanted to, I mean, I guess you could supplement. Well, let's go over here to they address that problem on contour maps by actually writing the altitude values every fifth line, it seems, right? And so that helps, but it is a problem. Yeah, absolutely. Okay. So and minor little quibble. Technically, the cross sections of the graph that I've got drawn here, if I compare the cross sections to the level sets, are they exactly the same thing? Well, I mean, one could quibble and say these are circles centered on x, y equals 0, 0, but elevated up in space, while these are circles centered at x, y equals 0, 0, living only in 2 dimensions. So, yeah, it's a little different. True, right? But it remains, though, that if you were to throw away the z component, in other words, if you were to project these down into the xy plane, those projections are the same as the level sets. Yeah.
And will they always start smaller and grow?
Now, it depends on the function. Yeah, it's always different. Every function's different. If the paraboloid, for example, was upside down, then the lower cross sections would be bigger, and as you go up, those cross sections, those therefore level sets would be getting smaller. Yeah, everyone's different. Yep. Yes.
Is change in z always perpendicular to the curve, the level set?
Say it one more time. I'm sorry.
It's like the change in the z-axis always perpendicular, like the fastest change in the z-axis.
I'm still not understanding.
If you're perpendicular to each of the circles, that would be the greatest increase in the curve, right? Like how you
I understand your question. Yes, and that's a much more sophisticated fact that we're going to get. We're going to conclude that once we've talked about something called gradients and directional derivatives. So you're several sections ahead on that. True fact, and we will get to it, but that's way ahead. Yep. Yeah. Okay. All right. Okay. So here's one of my favorite examples. This is one of my favorite examples because it shows how important it is not to confuse these constructions. And this is a recognition that when you're looking at if you have a function, there's several different pictures you can draw, or said differently, if you're looking at a picture, there's several different functions that you can use to describe it. So here it is. Now this example is I'm going to go through in detail here, but if you look through my old exams, you're going to find that there is a lot of analogous questions on my old exams. So FYI. Here we go. We've got the following line called L, about which I've given you some information. And I've given you the equation, right? And now I want to ask, what functions can I think of this as representing? Right now, a lot of people would say, I guess that function. And that's one of the answers, but there are several different answers. There are several different functions that I can use to represent this line. So let's start with the graph construction. I claim that this line is the graph of this function right here. Claim we're looking at the graph of that function. Now let me try to persuade you that this is the graph. Keep in mind how we do graphs. Graph says you're going to set this equal to a new variable. Now this is a function of only x, so new variable arbitrarily doesn't matter. I'm going to choose y. So this is what the graph looks like, the graph of that function that I just made up. And if you do just a little bit of algebra, what you will find is that equation and this equation are exactly equivalent. They're morally the same equation. And so, sure enough, this function represents that line. Specifically now, it is that this function, the graph of this function gives me this line. Right? Graph specifically. Okay. All right, now, by the way, how did I come up with this function? I didn't just pull it out of thin air. Where did it come from? Well, I know graphs. I know the deal with the dimensions and all, and so all of the variables together Well, there's two variables in this picture, so therefore the sum of these numbers has to be 2. And I also know that this is a one-dimensional curve, and thus there should be one input variable. So this number is 1, and they add up to 2, so therefore this has got to be 1 also. Right? So I know that it's a function of that sort. And now look at the algebra. Let's kind of reverse engineer this algebra. You can think of the relationship between these two equations going the other direction. You can think of it as, well, I kind of solved for y. Right? So that's a nice way to think about it. If you have an equation and you want to view it as a graph, solve for one of the variables. And having solved for one of the variables, it then is immediately in the form that you could say is, well, see, I've got something equal to a new variable. Well, that's what a graph is. Okay. All right. Okay, now here's the thing, though. This line is also a level set. It's a level set of this function here, and this one doesn't even require any algebra. I can see it in how it's already written, right? Level set, again, meaning we're setting some function equal to a constant. That's the algebra. It says there's this expression that I can call a function that has been set equal to a constant. And so this, which you note is a function from R2 to R1, is a function whose level set, one of whose level sets, is the exact same line. Okay, so now keep in mind, we already know that the same line it's the graph of this function, and now we see that it's a level set of that function. So, the kind of question that you might naturally ask is, okay, well, this line, which function is this line a picture of? And the answer is both, in different ways. What we're going to find is that when we start doing calculus, there are certain kinds of connections that we're going to draw, and this is coming up, soon-ish, but we do have a fair amount of stuff we have to do before we get there. But we will eventually find that the calculus of multivariable functions, and what does that look like geometrically, depends on what kind of a picture are you drawing. If you're drawing a graph picture, there are certain connections we're going to make between derivatives and what does that look like on the picture. And if we're looking at level sets, then there are totally different connections that we're going to make between derivatives and what does that look like on the picture. And so in order to know, should I interpret with the calculus of level sets or the calculus of graphs? Well, you better know whether you're looking at a graph or whether you're looking at a level set. And if you're not crisply clear on the difference between these two constructions, then you're going to accidentally apply the calculus of level sets to a graph, and you're going to get wrong answers. Does that make sense to everybody? Okay. I think another point that's worth noting here is how deceptively tricky this is. Right? If you look just at the actual algebraic manipulations, okay, well, I did 6th grade algebra to solve for y there. That's a joke, right? And here I didn't even solve anything. I just kind of recopied. And it's easy to look at this, therefore, and think, this is the easiest stuff in the world. The challenge with all of this stuff is not with the execution of the algebra. The challenge is in the proper use and interpretation of the language. So make sure to be very careful with how you use the language, because that's where you're going to get in trouble, and that's where you're going to get wrong answers. Okay. All right, lastly, same line. I can represent by this function. This is, in fact, just a parameterization of the function. In fact, you can see it right here, that point, 0, 2, and then plus t times this vector, which is 3, -2. You can see it right there in the algebra there. So this line is parameterized by this yet now third function. Same line. So, and just like with graphs and level sets, we're going to have a calculus of parametric curves, right? So the calculus of graphs and the calculus of level sets and the calculus of parametric curves, they're all different. And so again, knowing which one to use requires knowing which kind of a picture you're looking at, which means understanding all of these subtleties. Okay, is everybody happy? Is everybody following me? Everybody good? Okay. All right. Okay, so I've actually already kind of talked through this business here. Anyway, let me go ahead and observe. We know that derivatives give slopes, right? Ancient history. Derivative equals slope. Ooh, careful. Pause. Derivatives gives you slopes if you're looking at a graph. So that statement, derivative equals slope, that's part of the calculus of graphs. And it works here, right? If you were to take the derivative of this, you get minus 2/3, and that is indeed the slope of that line. Yes, cool. Derivative equals slope. If you're looking at a graph, but I ask now, what if we weren't doing graphs? What if I was thinking in terms of level sets? Is the derivative of this equal to that slope? Oh, no. Not remotely. In fact, we don't technically even yet know how to take derivatives of these kinds of functions. And when we do, those derivatives will not equal to this slope. So, again, careful. All right. Okay, here's a neat fact relating graphs and level sets. Turns out every graph is a level set. This is a wonderful little observation that's useful in a lot of circumstances. And before I show you how it works, let me tell you why we would care. Sometimes you're looking at a graph, but the thing that you need to know about that picture is you need to understand something that the calculus of level sets would be just perfect, right? It's like you need to do the calculus of level sets, but you don't have your thing written as a level set. So knowing that every graph can be turned into a level set, thus allowing you to use the calculus of level sets, can be really, really important. Right? So anyway, here's how you do that. This is a very literal. Again, the only thing that's tricky about this is the careful use of language. But if you have a graph, and keep in mind what a graph is. Graph says I'm going to set the function equal to a new variable. So there's how I represent that I'm looking at a graph. I'm looking at a graph of specifically this function called f that has n input variables. And that graph has this equation right there. Right. Here's what you do. Again, it's really very easy in terms of the algebra. All you got to do is just kind of move with the right-hand side over the left-hand side. Just kind of subtract everything over. And by the way, you can go the other direction if you want. It doesn't really matter. Here, I've taken the right side and subtracted it over to the left. And ta-da! So, in fact, we're about to notice that I have converted a graph to a level set. And here's why. Check it out. Stuff equals a constant. That's what a level set is. I've rewritten my algebra as stuff equals a constant. Now, very importantly, it's not the same stuff. This thing whose level set I'm looking at, this is not f. Right? That's a new function. For one thing, it's got an extra variable in it. Right? This thing on the left that I'm setting equal to 0 has n plus 1 variables. It's got all of those x variables, x1 through xn, and y. Also part of that same set of input variables now. So, different function. So what's kind of nice about this then is, again, how easy the algebra is. I just, this one little algebraic trick. And it allows me to take a circumstance in which initially I'm confined to using the calculus of graphs because it's only this one little function f that I know, and the thing in question is the graph of this, and I guess I'm doing calculus of graphs. But one little tweak, and now I can rephrase the question as a statement about level sets, and I can use the calculus of level sets. And granted, we don't yet know, right, the calculus of level sets, but we will very soon. So this is how you convert one question into a different question. How are we doing? Everybody with me? All right. Okay, let's see an example of this in action. Here's what I'm going to start with. I'm looking at a graph of a given function. Again, graph because, well, z equals. Right? And I'm looking at a graph specifically of this function here. And very important, by the way, we're not looking at the graph of z equals x squared plus y squared. That's an equation. This is an equation. We are not looking at the graph of that equation. We're looking at the graph of this function. Right? Okay. Graph means this part. So saying graph of an equation that has the graph of construction already in there, it's kind of like saying Rio Grande River. I don't know if y'all have ever thought about that one. Rio means river. So Rio Grande River that doesn't make any sense. Anyway. Okay. All right. Now notice I do my little algebraic fast one. Just subtract the right side over to the left side, and now, lo and behold, I got myself a level set. Right? This is a particular level set. This is the G inverse of 0 level set, but specifically now, new function that I can think in terms of. I can understand the original question that was asked, whatever it was, whatever I wanted to know about this surface. I can now use the calculus of level sets applied to this function. In addition to, I can also use the calculus of graphs applied to that function. So I got options now. Everybody on board? Okay. All right. Now, notice this is a one-directional deal. Not every level set is a graph. If you have a level set, you might be able to rewrite it as a graph, but you might not. And keep in mind, if you wanted to rewrite something as a graph means you need to solve for one of the variables. I need, y equals or x equals, something equals, right? Some function. And you just can't do that sometimes. In fact, I'd say often can't do that. So, for example, let's look at this one right here. Here's an equation. This is a level set. Right? I've got stuff equals constant, so I can view this. I can do calculus of level sets all day long, no problem. But can I use the calculus of graphs here? No. I can't solve for y. I get two different values. That's not what... In situations like this, when we say solve, we mean solve for a single uniquely existing value. And there are just either two values of y or 0 values of y, but except for very rare circumstances, there is not just a single value of y. So graph, not on the table. Everybody happy? Everybody remember the vertical line test, by the way? I hope this is a memory from long ago, but the vertical line test, in order for something to be a graph, you need for vertical lines to intersect the curve exactly once. And fail here. Okay. All right. Okay, so we're going to move on now and do a little bit of algebra. By the way, this section that we're in is a very long section, and we're no way are we going to finish that in the next minute and 9 seconds. So we're probably not going to finish any sections today, and hope we'll finish it on Monday. We'll see. So anyway, I just want to end with a real quick observation about rotational symmetry. If you have some equation, a rectangular equation, and if x and y appear only as a part of this very specific construction, square root of x squared plus y squared, if that happens, if you can write your equation where x and y don't appear anywhere in the equation other than as part of that specific form, and by the way, that's pretty easy to notice at a glance. Just look at your x's and y's and see, are they all stuck inside of one of these forms? If so, this very easily observed trait instantly gives you this powerful geometric information about your equation, namely the picture is rotationally symmetric. And the idea is that look at a couple of points that are rotations of each other. You got this point here, and we got this point here, and they have different x's and y's. These are not the same points. And if you were to plug these points into a generic equation, you would assume that you would get different answers because they are different points with different coordinates. But the thing is, in such an equation, these x's and y's give me the same value of r because they're rotations of each other. And that's the only way x's and y's show up. They also have the same z coordinate because they're rotations of each other. And so these 2 points are going to do the exact same thing in the algebra. Even though they're different points, they will perform identically in the equations. And so they're either both on my surface or they are neither on my surface. Does that make sense? All right, and we'll talk later about a different point of view on this and how to capitalize. Okay, see y'all later. Have a good weekend.